Hi, my name is Ben Loveday and welcome to the next in our series of machine learning Jupyter notebooks for dealing with ocean data. In this instance, we're going to be looking at how to use machine learning approaches to combine Sentinel-2 and Sentinel-3 chlorophyll retrievals in coastal waters. This notebook was edited and authored by myself, Ben Loveday from InnerFlare, based on the work by Nima Pallavan and Brandon Smith from NASA and their colleagues. Let's take a look at our notebook. As before, at the top of the notebook you will find a short video, the one I'm recording for you now, which shows how to use this notebook, and you should feel free to refer back to it at any point. So let us begin with an introduction. Why are we doing this? When we want to monitor any ocean or environmental phenomenon, one of the key things we must consider is how many measurements we need to take and how often we need to take them. Satellites offer us great advantages for environmental monitoring. We can measure multiple times per day to multiple times per week or month. And year on year, ever increasing resolution. Sentinel-2 can now monitor at 10 meter resolution, Sentinel-3 at 300 meter resolution, and we can use this 300 meter resolution scale globally. However, because of instrument and satellite platform engineering, orbital requirements, data transfer, etc., there are nearly always compromises to be made between whether or not we get spatial, temporal or spectral resolution in our missions. And to optimize our monitoring approaches, we need to try and find ways of combining this information to take advantage of the best of all worlds. The challenges of managing coastal and inland water quality, which we have discussed in previous notebooks, are an example of where the use of multiple data sources can bring substantial benefits. However, combining these sources can be difficult. The way the instruments measure their sensitivities and resolutions have to be accounted for to create data sets that can be appropriately interpreted by decision makers. What will this workflow show you? This workflow will show you how to apply an in situ trained mixture density network to data from 2 Copernicus satellites to provide seamless estimates of chlorophyll concentration in coastal regions. We will use data from 2 sources, from the MSI instrument aboard Sentinel-2 and from the OLCI instrument aboard Sentinel-3. At the core of this notebook is the mixture density network machine learning algorithm, in this case deployed using Keras. MDNs are a class of neural network where the outputs of a network are used in the parameterizations of Gaussians, giving a probability distribution of the target variable over a given region. This is particularly useful where you have non-unique inverse problems, such as the case with ocean color, where we can reconstruct a given spectra using many different in-water constituents. We call this spectral ambiguity. The MDN we use is developed by NASA. We're using a subset of this MDN machine learning library here, but the full model is available via this Git clone link. The pre-trained model used in this example was generated using thousands of co-located pairs of in situ data of chlorophyll concentration and remote sensing reflectance. This model is pre-trained for our purposes, and for full details you can see Pallavan et al. 2020. In terms of data, we'll be using data from 2 sources. We will be using data from an OLCI full resolution level 2 scene for the Baltic Sea. This is gathered at 11 minutes past 9 on the 20th of April 2021 with standard atmospheric correction. We will also be looking at an MSI level 2 scene from Sentinel-2 for the Baltic Sea at 1 hour later, 10 AM on the same day, also with standard atmospheric correction. In addition to the images above, we've also processed both of these using the HyGeos polymer atmospheric correction method. We will discuss why we've performed this task later. You can find further resources on these approaches and on the MDN algorithm itself in the section of further resources. So let's move on to our notebook itself. What steps are we going to perform as part of the notebook? Firstly, we're going to compare OLCI and MSI as sensors. Secondly, we'll prepare our experiments. Thirdly, we'll test our MDN model. Then we will run it and we will compare the outputs. And finally, we will conclude. As before, we will begin by importing all the libraries we need to complete our task. In box number 2, we import all the standard Python libraries we will require. And in box number 3, under defined functions, we'll import the functions that we have made. So we're going to import functions called ocean support functions 4G. This will help us managing plotting and preparing some of our input data. You can find ocean support functions 4G.py in the same folder as this if you wish to have a look at these functions. We will also import from MDN, the package, the required methods we need to complete our machine learning task. So we'll import 3 methods: image estimates, get tile data, and get sensor bands. Image estimates is the most important one for our purposes. That's the one that actually launches the model. So let's compare OLCI and MSI data. Sentinel-3 OLCI is the ocean color workhorse of the Copernicus fleet. It is our go-to sensor for looking at ocean scenes and retrieving ocean parameters from space. It was specifically designed to monitor the ocean, and it's regularly used in monitoring coastal systems. While nominally designed for land use, the high resolution of Sentinel-2 MSI also makes it a useful tool for monitoring the coasts. However, the two are very different and combining data from them is challenging. Let's take a little look at why. Figure 1 compares the same scene off the southwest coast of the UK, a coccolithophore bloom in this case, from both Sentinel-3 OLCI on the right and Sentinel-2 MSI on the left. And you can see there's a notable difference in spatial resolution in these cases. Sentinel-2 is significantly higher. This also has an effect on how this natural colour is perceived, as there are different response functions associated with each sensor. So potentially at this point you will be thinking point to MSI, much higher spatial resolution. However, when we compare from a spectral perspective, we can see from figure 2 that the situation is reversed. MSI on the right has much wider and much fewer bands useful to us in the ocean realm than OLCI does. OLCI has 21 spectral bands. These bands are much narrower, they're much more specific, and from an ocean colour science perspective, they're much more useful to us in terms of deriving in water properties. So after figure 1 and figure 2 are combined, it's kind of point to OLCI really. OLCI is our go-to sensor. What we'd like to do though is take advantage of the spatial resolution of Sentinel-2. So ideally what we want is a method where we can combine the capabilities of both to give us a harmonized chlorophyll retrieval irrespective of the sensor that we're going to use, and that's what this MDM method will show us how to do. So let us go ahead and prepare our experiments. We've chosen the Baltic Sea for a reason. It's highly complex. Consequently, we need to ensure that we do everything possible with the input data to make sure that the model has a good chance of retrieving a reliable chlorophyll estimate. We are going to group our experiments into two sets. Set 1 will deal with MSI and OLCI processed using their standard atmospheric processors. For the OLCI level 2 product, this processor is already specific and appropriate to the marine environment. However, for MSI, the standard atmospheric processor is geared predominantly for land, which makes it somewhat challenging to use for the ocean. There are specific atmospheric processors out there for Sentinel-2 for the ocean, and I encourage you to look at either C2RCC or Acolyte or Polymer if you're looking to use MSI in the ocean region. Because of this reason, set 2 will be the same experiments, but we will run with MSI and chlorophyll data that's been atmospherically corrected with the HyGeos Polymer atmospheric processor. If you read NEMA's paper, which was referred to earlier, Palavan et al. 2020, you will find that this approach actually gives much better chlorophyll retrievals, and that's why we've decided to adopt it here. So in total, we're going to run 4 experiments, 1 standard and 1 polymer run for each of OLCI and MSI. So box 4 will set up these experiments. All we're doing is constructing a series of dictionaries that contain the information on the experiment we're going to run. Each experiment has an input product, a processor name, a sensor, an RRS correction term, and this variable called OLCI coords. All OLCI coords is a subset spatial box we're using to cut down both our Sentinel-2 and our Sentinel-3 scene so that we're looking at roughly the same area. For this example, and because we're running on the Wekio architecture, to keep our data requirements and processing requirements slightly minimized, we're going to be running with Sentinel-2 at 60 meters, not 10 meters, which Sentinel-2 can provide. Sentinel-3 will be run at 300 meters, the native resolution of the instrument. So before we proceed any further, we might want to get an idea of how long this takes the model to run. The model itself is relatively complex, so we're going to just test it with some random data. So in box 5, we're setting up a random array of values between 0 and 1, and then I'm dividing them by a factor of 1,000 just to give us roughly an order of magnitude that's kind of similar to what we'd expect from an RRS, or remote sensing reflectance, just to see what sort of chlorophyll concentrations are retrieved. I'm purely doing this so we can test how long it takes to run on our system. So when we run this, we'll see that when I run with my tile size of 100 by 100, so 10,000 points, the model takes 16 seconds. nice and quick, but a standard OLCI image has somewhere between 4,000 by 4,000. So off the top of my head, I'm guessing that's about 16 million points that we may end up processing. So we do need to factor in how heavy some of this processing might be and act accordingly. Just to give you an idea of what that randomized data looks like, unsurprisingly, there's no spatial pattern here. We've not really encoded one in our randomness, but it does give us chlorophyll concentrations of between 0 and around about 130 milligrams per meter cubed, which are feasible values for the RRSs, the remote sensing reflectances we fed the model with. So let's now proceed with running the MDN model for our actual data. We're going to begin with our standard experiments and start with Sentinel-3. In box 8, we are reading in our Sentinel-3 data in accordance with what we specified in our experiments, using this method read S3L2 standard. This will return to us the Sentinel-3 remote sensing reflectance and the longitude and latitudes of our scene. To launch that data, all we then need to do is call this image estimates method from the MDN library that we imported earlier. And this will give us estimates S3. We're going to do exactly the same for our Sentinel-2 standard atmospherically processed data to give us estimates S2. And we can see that when we read in and run both of these, the bands that are red are appropriate for each sensor. Now that we have our output, let's compare the results. The box below, box 10, will plot our OLCI and MSI chlorophyll estimates side by side. This is all this box does. And here are the results. So on the left hand side we have MSI chlorophyll concentrations at 60 meter resolution, and on the right hand side we have OLCI 300 meter resolution chlorophyll concentration estimates. These products are currently on different grids, a 300 meter grid for OLCI and a 60 meter grid for MSI. To compare the anomaly between them, we need to interpolate the MSI data onto the OLCI grid, and we'll do this in box 11. Once we've done this in box 12, we can look at the anomaly between the two. So box 12 produces the plot figure 6, which is the anomaly between our OLCI and MSI chlorophyll estimates with standard atmospheric processing. And we can see that there's still substantial anomalies. There's not the seamless retrieval we'd hoped. There are some reasons to explain this. The first reason is we have used standard atmospheric processing, which we know for Sentinel-2 is not ideal. The second thing is these images are gathered 1 hour apart. In the Baltic Sea, that's easily enough time for there to have actually been dynamic variability in the system itself, so we should never expect there to be zero anomaly. But this is perhaps more than we would have hoped for before. Let's try again with our polymer atmospheric processing and seeing if we can do better. So moving on to our polymer experiments, we are going to do exactly as we did for the set 1 of experimentation. We're going to calculate estimates S3 poly using the image estimates from the OLCI scene processed with polymer, and the same with Sentinel-2 to give us estimates S2 poly. As before, once we have these two estimates, we want to interpolate them onto the same grid so that we can do a direct comparison between the two. Box 15 will interpolate the MSI data onto the OLCI grid to give us S2 interp chlorophyll poly, and then we can use that to plot the same anomaly as we did before. And as we can see from the final plot, there's a notable improvement. Using atmospheric correction methods that are appropriate for the marine environment, we actually drop our anomaly to very, very low values between OLCI and MSI. This makes this a very, very powerful tool for us to use, as we can come up with consistent estimates from whatever satellite happens to be overpassing the region at any time. However, we can still see some small anomalies that occur, mostly to do with spatial patterns that look like they correspond to dynamic variability in a given feature that's relatively near the coast. We would never expect these to align completely unless potentially we had exact overpass times that corresponded to each other, and in practice that's almost certainly never going to happen. In conclusion, our coastal oceans are highly complex. To give us the most comprehensive picture, we need to take advantage of the spatial and spectral resolution of multiple satellites. Machine learning approaches such as mixture density networks allow us to combine data in ways which reinforce our ability to monitor the coastal region and give us improved information for policy making and decision makers.